स्टूडेंट्स, ਅੱਜ ਦੀ ਕਲਾਸ ਵਿੱਚ ਤੁਹਾਡਾ ਸਵਾਗਤ ਹੈ। ਜਿਵੇਂ ਕਿ ਤੁਸੀਂ ਸਾਰੇ ਜਾਣਦੇ ਹੋ ਕਿ ਕੈਮੀਕਲ ਸਿੰਥੇਸਿਸ ਦਾ ਇੱਕ ਪ੍ਰਿੰਸੀਪਲ ਗੋਲ એનર્ਜੀ ਦਾ ਐਕਸਪੈਂਡੀਚਰ ਮਿਨੀਮਾਈਜ਼ ਕਰਦੇ ਹੋਏ ਰਿਐਕਟੈਂਟਸ ਦੇ ਪ੍ਰੋਡਕਟਸ ਵਿੱਚ ਕਨਵਰਜਨ ਨੂੰ ਮੈਕਸਿਮਾਈਜ਼ ਕਰਨਾ ਹੈ। That means ਮਾਈਲਡ ਟੈਂਪਰੇਚਰ ਅਤੇ ਪ੍ਰੈਸ਼ਰ ਤੇ ਮੈਕਸਿਮਮ ਯੀਲਡ ਪ੍ਰਾਪਤ ਕਰਨਾ ਹੈ। ਇਸ ਗੋਲ ਨੂੰ ਅਚੀਵ ਕਰਨ ਲਈ ਐਕਸਪੈਰੀਮੈਂਟਲ ਕੰਡੀਸ਼ਨਸ ਨੂੰ ਜਨਰਲਾਈਜੇਸ਼ਨ ਦੇ ਆਧਾਰ ਤੇ ਐਡਜਸਟ ਕਰਨ ਦੀ ਲੋੜ ਪਈ, ਜਿਸ ਨੂੰ ਬਾਅਦ ਵਿੱਚ ਲੀ ਚੈਟਲੀਅਰਸ ਪ੍ਰਿੰਸੀਪਲ ਦੇ ਨਾਂ ਨਾਲ ਜਾਣਿਆ ਗਿਆ, ਜੋ ਕਿ ਸਾਡਾ ਅੱਜ ਦਾ ਟੌਪਿਕ ਵੀ ਹੈ। ਪਰ ਅੱਗੇ ਵਧਣ ਤੋਂ ਪਹਿਲਾਂ ਅੱਜ ਦੀ ਕਲਾਸ ਦੇ ਲਰਨਿੰਗ ਆਬਜੈਕਟਿਵਸ ਜਾਣ ਲਈਏ।
On completion of this topic, learners will be able to define Lee-Chatelier's principle, discuss Lee-Chatelier's principle, apply Lee-Chatelier's principle in various chemical reactions.
ਲੀ-ਚੈਟਲੀਅਰਸ ਪ੍ਰਿੰਸੀਪਲ 1884 ਵਿੱਚ ਫਰਾਂਸੀਸੀ ਵਿਗਿਆਨੀ ਹੈਨਰੀ ਲੀ ਚੈਟਲੀਅਰ ਅਤੇ ਬ੍ਰੌਨ ਨੇ ਇੱਕ ਜਨਰਲ ਪ੍ਰਿੰਸੀਪਲ ਇੰਟਰੋਡਿਊਸ ਕੀਤਾ, ਜੋ ਕਿ ਸਾਰੇ ਸਿਸਟਮਸ ਦੀ ਇਕੁਇਲਿਬਰੀਅਮ ਸਟੇਜ ਵਿੱਚ ਲਾਗੂ ਹੁੰਦਾ ਹੈ। ਹਾਂ ਬੱਚਿਓ, ਇਸ ਮਹੱਤਵਪੂਰਨ ਨਿਯਮ ਨੂੰ ਲੀ ਚੈਟਲੀਅਰਸ ਪ੍ਰਿੰਸੀਪਲ ਕਿਹਾ ਜਾਂਦਾ ਹੈ। ਇਹ ਦੱਸਦਾ ਹੈ ਕਿ ਚੇਂਜ ਇਨ ਐਨੀ ਆਫ ਦ ਫੈਕਟਰਸ that determine the equilibrium conditions of a system will cause the system to change in such a manner so as to reduce or to counteract the effect of change. Or when a stress is applied on a system in equilibrium, the system tends to adjust itself so as to reduce the stress. ਇਹ ਸਿਧਾਂਤ chemical equation ਦੇ equilibrium ਤੇ effect of concentration change, effect of pressure change, effect of temperature change, effect of inert gas addition ਦਾ ਅਨੁਮਾਨ ਲਾਉਣ ਲਈ ਸਹਾਇਤਾ ਕਰਦਾ ਹੈ। So another definition is, if a change in the concentration, pressure or temperature is caused to a chemical reaction in equilibrium, the equilibrium will shift to the right or the left to minimize the change. Let us first discuss the effect of concentration change. According to Lee-Chatelier's principle, when concentration of any of the reactants or products is changed, the equilibrium will shift in a direction to reduce the effect of change in concentration that was made. Let us try to understand the effect of increasing concentration with the help of this animation.
Here reactants A and B combine to form product C. This symbol shows that the reaction is reversible. When a reactant A is added at equilibrium, its concentration is increased. The reaction takes place in forward direction. Thus, addition of A causes the equilibrium to shift to right.
Thus, the concentration stress of an added reactant or product is relieved by the net reaction in the direction that consumes the added substance, that is, the increase in concentration of any of the reactants shift the equilibrium to forward direction. Now let us see the effect of decreasing concentration with the help of this animation.
When a reactant A is removed at equilibrium, its concentration is decreased. The reaction takes place in backward direction. Thus, removal of A causes the equilibrium to shift to the left.
Thus, the concentration stress of a removed reactant or product is relieved by the net reaction in the direction that replenishes the removed substance, that is, the decrease in concentration of any of the products shifts the equilibrium to forward direction. Let us discuss it in detail with the help of examples.
Here, 1 mole of nitrogen reacts with 3 moles of hydrogen to form 2 moles of ammonia. When nitrogen is added to the reaction, which is already in equilibrium 1, it tries to shift equilibrium to the right, so as to reduce the concentration of nitrogen according to Chateliers principle.
Students, let us have a look at an animated chart.
Equilibrium 1 and equilibrium 2 are shown in this table. At equilibrium 1, concentration of nitrogen, hydrogen and ammonia is shown. On addition of 1 mole per liter of nitrogen to reaction mixture, it shifts to equilibrium 2. In equilibrium 2, it is observed that concentration of ammonia increases, while concentration of hydrogen decreases. Thus, to obtain a high yield of ammonia, one of the reactants should be added in excess.
Let us now discuss the effect of pressure change. According to Chateliers principle, when pressure is increased on a gaseous equilibrium reaction, the equilibrium will shift in a direction
having less number of gaseous moles or molecules.
Let us try to understand the effect of increasing pressure with the help of this animation.
Here reactants A and B combine to form product C. This reaction is reversible.
We know that the pressure of a gaseous reaction at equilibrium is determined by the total number of molecules it contains. Let us again have a look at this animation.
Thus, when the pressure is increased, the equilibrium will shift to right side. That is, more C molecules are produced because in forward direction, 2 reactants are taking part and one product is formed.
Thus, increase of pressure on a chemical equilibrium shifts it in that direction in which the number of gaseous molecules decreases. But what happens when pressure is decreased?
When pressure is reduced, reactants will form more and the equilibrium will shift to backward direction. That means A and B will form more.
Let us understand this in another way.
Thus, decrease of pressure on a chemical equilibrium shifts it in that direction in which the number of gaseous molecules increases. Let us consider a chemical reaction. Here, 2 molecules of chlorine in gaseous state reacts with 1 molecule of phosphorus trichloride in gaseous state to form 1 molecule of phosphorus pentachloride in gaseous state. Initially, 3 molecules of chlorine gas, 3 molecules of phosphorus trichloride and 1 molecule of phosphorus pentachloride, total 7 molecules are shown on the screen. But what happens when pressure is applied? Equilibrium shifts to the right in forward direction, resulting in 2 molecules of chlorine gas 2 molecules of phosphorus trichloride and 2 molecules of phosphorus pentachloride, total 6 molecules. If more pressure is applied, total number of molecules is reduced to 5, with 1 molecule of chlorine gas, 1 molecule of phosphorus trichloride, and 3 molecules of phosphorus pentachloride. Further, shifting equilibrium towards right, that is towards less number of molecules, thereby decreasing pressures. Now what happens when pressure is reduced? The number of molecules again changes, generating 2 molecules of chlorine gas, 2 molecules of phosphorus trichloride, and 2 molecules of phosphorus pentachloride, total 6 molecules. If more pressure is reduced, it turns as 3 molecules of chlorine gas, 3 molecules of phosphorus trichloride, and 1 molecule of phosphorus pentachloride, total 7 molecules. Thus shifting equilibrium in backward direction, that is towards more number of molecules, thereby increasing pressure.
Let us try to understand this with the help of examples.
Iodine gas is shown in equilibrium with iodide ions at high temperature. Let us look at micro level. Iodine molecules and iodide ions are shown here. Let us look at a chart showing concentrations of iodine gas and iodide ions. What happens when pressure is increased? When pressure is increased, reaction moves in backward direction. The reason is pressure is proportional to number of moles. Concentration of iodide ions decreases. As a result, concentration of iodine increases. Decreasing concentration of iodide ions and increasing concentration of iodine molecules is shown in the graph. After some time, equilibrium is established.
What happens when pressure is decreased? Let us try to know with the help of this animation.
When pressure is decreased, reaction moves in forward direction. As we know that the pressure is proportional to number of moles. Concentration of iodide ions increases. As a result, concentration of iodine molecules decreases. Increasing concentration of iodide ions and decreasing concentration of iodine molecules is shown in the graph. After some time, equilibrium is established.
To sum up, we can say that increase in pressure shifts the equilibrium in the direction of lesser number of gaseous moles, and decrease in pressure shifts the equilibrium in the direction of larger number of gaseous moles. Now it's time to discuss effect of temperature change. But before taking up this, it's time to recall reaction types. Students, chemical reactions ਵਿੱਚ opposing processes ਹੁੰਦੀਆਂ ਹਨ। ਇੱਕ ਨੂੰ forward reaction ਅਤੇ ਦੂਜੀ ਨੂੰ backward reaction ਕਿਹਾ ਜਾਂਦਾ ਹੈ। ਜੇ heat ਨਿਕਲਣ ਨਾਲ forward reaction ਅੱਗੇ ਵਧਦੀ ਹੈ ਤਾਂ ਇਸ ਤਰ੍ਹਾਂ ਦੀ reaction ਨੂੰ exothermic reactions ਕਿਹਾ ਜਾਂਦਾ ਹੈ। ਪਰ backward reactions ਵਿੱਚ ਇਸ ਦੇ ਉਲਟ ਪ੍ਰਭਾਵ ਵੇਖਿਆ ਜਾਂਦਾ ਹੈ। backward reaction heat ਸੋਕਣ ਨਾਲ ਹੁੰਦੀ ਹੈ। ਇਸ ਤਰ੍ਹਾਂ ਦੀ ਰਿਐਕਸ਼ਨ ਨੂੰ ਐਂਡੋਥਰਮਿਕ ਰਿਐਕਸ਼ਨ ਕਿਹਾ ਜਾਂਦਾ ਹੈ। ਇੱਥੇ ਇਹ ਧਿਆਨ ਦੇਣ ਯੋਗ ਹੈ ਕਿ ਫਾਰਵਰਡ ਅਤੇ ਬੈਕਵਰਡ ਰਿਐਕਸ਼ਨਸ ਇੱਕ ਹੀ ਸਮੇਂ ਤੇ ਹੁੰਦੀਆਂ ਹਨ ਅਤੇ ਇਹਨਾਂ ਦੋਹਾਂ ਦਰਮਿਆਨ ਇਕੁਇਲਿਬਰੀਅਮ ਬਣਿਆ ਰਹਿੰਦਾ ਹੈ। So according to Chatelier's principle, when temperature is increased in a chemical reaction, the equilibrium will shift in a direction in which heat is absorbed, or the increase of temperature favors the reverse change in an exothermic reaction and the forward change in an endothermic reaction. Let us see the effect of increasing temperature on chemical reaction with the help of animation.
Reactants X and Y absorb some heat and product Z is formed. What will be the impact of increasing temperature on it? As we know, when temperature is increased in a chemical reaction, the equilibrium will shift in a direction in which heat is absorbed. As a result, the equilibrium will shift in forward direction.
Thus, increase in temperature shifts the equilibrium in forward direction. Let us now take up exothermic reaction.
Suppose X and Y combine to form Z and heat is released. As we know, when temperature is increased in a chemical reaction, the equilibrium will shift in a direction in which heat is absorbed. As a result, the equilibrium will shift towards the left-hand side or backward direction.
Thus, decrease in temperature shifts the equilibrium in backward direction. Now let us understand this further with the help of animation.
Dinitrogen tetraoxide in gaseous state and heat is shown in equilibrium with nitrogen dioxide gas. This process is also known as dimerization of nitrogen dioxide gas. At micro level, nitrogen dioxide molecules and dinitrogen tetraoxide molecules are shown at equilibrium. Let us look at a graph showing concentration of nitrogen dioxide molecules and dinitrogen tetraoxide molecules. When temperature is raised, heat acts as a reactant. Reaction moves in forward direction. As a result, concentration of nitrogen dioxide molecules increases and concentration of dinitrogen tetraoxide decreases. After some time, equilibrium is reached. When temperature is lowered, heat acts as a product. Reaction moves in backward direction. As a result, concentration of nitrogen dioxide molecules decreases and concentration of dinitrogen tetraoxide increases. After some time, equilibrium is reached.
Next is the effect of addition of inert gas. What happens on addition of an inert gas to an equilibrium mixture at constant volume and constant pressure? Let us discuss one by one. When an inert gas such as argon is added to the equilibrium system at constant volume, then total pressure will increase. But the concentrations of the reactants and products will not change. Hence, under these conditions, there will be no effect on the equilibrium. Why is it so? Because it does not take part in the chemical reaction. Hence, the addition of an inert gas at constant volume does not change the partial pressures or the molar concentrations of the substance involved in the chemical reaction. The reaction quotient changes only if the added gas is a reactant or product involved in the reaction. When an inert gas is added to the equilibrium system at constant pressure, then volume will increase. As a result, the number of moles per unit volume of various reactants and products will decrease. Hence, equilibrium will shift in a direction in which there is increase in the number of moles of gases. Another is the effect of catalyst. Catalyst does not shift the equilibrium in any direction. A catalyst does not affect the state of equilibrium and the value of equilibrium constant remains the same, no matter whether the catalyst is used or not. The reason is because a catalyst catalyzes both forward and backward reactions to the same extent. As a result, the values of the rate constants for forward and backward reactions increase to the same extent. Therefore, the value of equilibrium constant remains the same. So, the catalyst does not change the equilibrium constant. It simply helps to attain the equilibrium faster. As we have discussed Lee-Chatelier's principle in detail, let us now discuss conditions for maximum yield in the industrial processes. We know that ammonia is prepared by Haber's process. Relevant chemical reaction is shown here.
One mole of gaseous nitrogen reacts with 3 moles of gaseous hydrogen to form 2 moles of gaseous ammonia, and 22 kilocalorie heat is evolved. So, this reaction is exothermic. The number of moles is 4 on the left hand side and the number of moles is 2 on the right hand side. Hence, the number of moles is less on the right hand side. Thus, favorable situations are low temperature. According to Lee-Chatelier's principle, at low temperature, equation shifts to the right to give more amount of ammonia. Next is high pressure. According to Lee-Chatelier's principle, at high pressure, equation shifts to the right to give more amount of ammonia. The reason is the number of moles are less on the right hand side. Catalyst. At low temperature, the rate of reaction remains low and equilibrium establishment takes a longer time. To increase the rate of reaction and for quick establishment of equilibrium, a catalyst is used. Finely divided iron containing less amount of molybdenum is used in actual practice. In this case, molybdenum acts as a promoter. It helps in the life and efficiency of the catalyst.
Let us now discuss conditions for maximum yield on nitric oxide. Let us have a look at the chemical reaction shown on the screen.
One molecule of gaseous nitrogen reacts with one molecule of gaseous oxygen to form 2 molecules of nitric oxide and 43.2 kilocalories heat is absorbed in this reaction. So the reaction is endothermic. The number of moles is equal on both sides. Favorable situations for this chemical equation are high temperature. According to Lee-Chatelier's principle, at high temperature, equation shifts to the right to give more nitric oxide. No effect of pressure. As per Lee-Chatelier's principle, the forward reaction involves no change in the number of moles. So we can say that a change in pressure does not affect the equilibrium. High concentration. According to Lee-Chatelier's principle, the formation of nitric acid is favored by using high concentrations of the reactants.
Students, it is time to check your knowledge. Here I am giving some questions. Try to answer them. Let us look at some reversible chemical reactions.
How will an increase in pressure affect the shown chemical equilibria? Please compare the number of molecules on both sides of the chemical reaction equation. If those numbers are different, the reaction proceeds in the direction giving the smaller number of molecules. If the numbers are equal, pressure does not affect the equilibrium. Answer: absolutely correct. In the first chemical equation, equilibrium shifts to the left. In the next chemical equation, equilibrium shifts to the right. In the next chemical equation, equilibrium remains unchanged. In the next chemical equation, equilibrium shifts to the right. In the next chemical equation, equilibrium shifts to the right. In the next chemical equation, equilibrium shifts to the left. The next question is, examine the given equilibria. How would you change the pressure in each case so as to obtain a high yield of the product? Answer: in this chemical reaction, the number of molecules on the left-hand side of the chemical equation is larger than the number of molecules on the right-hand side of the chemical equation. It requires increase in the pressure. In this chemical reaction, the number of molecules on both sides of the chemical equation are equal. Pressure does not affect the equilibrium. In this chemical reaction, the number of molecules on the right-hand side of the chemical equation is larger than the number on the left-hand side of the chemical equation. It requires decrease in the pressure.
स्टूडेंट्स मैनू उम्मीद है कि तुसी भी अज दे लैसन नू उन्ना ही इंजॉय कीता होवेगा जिन्ना कि मैं कीता है। ध्यान देने लई बहुत बहुत धन्यवाद। फिर मिलांगे।